Hi children, today let us see the first unit of electrostatics. And electrostatics is a very interesting topic, and you can see three demonstrations on the screen. Left is the styrofoam beads getting attracted to the hand. Next you can see a balloon sticking onto the hair of the person, and the third is a cat. And all these are applications of electrostatics. Just see the word electricity. Electricity is a form of energy, just like other forms of energy, and this electricity can be classified into two: static electricity and current electricity. See, static electricity means study of charges at rest, and current electricity means study of charges in motion. And as seen in the picture, we can see static means charges at rest and current electricity means charges in motion. First chapter, electrostatic fields and charges. To begin with, let us see the structure of atom that you have studied in lower class. In the atom there are protons, electrons and neutrons. Protons are positively charged, electrons are negatively charged, and charge is a fundamental property of matter which is associated with the production of electric field and magnetic field. There are two types of charges, positive charge and negative charge, and the name of the charges, positive and negative, is named by a scientist whose name is Benjamin Franklin. And about the scientist, you might have heard of a story.
He had made a special kite which was made up of silk cloth, because he knew that on stormy days what happens is the speed of the wind is so high that it can damage the kite, so the kite had to be strong. So the body of the kite was made by silk cloth. Then he took a hemp rope, long hemp is shown over here in this diagram, and hemp rope is an insulator. Now on the top he attached a very thin and pointed iron rod on the top part of the kite. Now here, just near to his hands, he took a silk rope and connected with the hemp rope, and here very near to his hand there was a key like this. Like this one. Now Benjamin Franklin knew that when during this season it might happen that rain could come, and this rain will definitely wet up this hemp rope, and if this kite goes very near to the clouds, then it is going to draw the electrical charges, and those charges would now pass through the hemp rope now, because it is no longer an insulator, because it is now wet. So he may get a shock. So to prevent himself, he attached the last part of the rope with a silk cloth. Now silk cloth is actually a insulator, and he made himself insulated by staying under a roof, right? So let's try to understand the entire experiment now. So this is the Franklin's experiment, where he is actually inside a particular place, and he kept himself insulated, and these are the clouds. Now this is the pointed iron rod, this is the key, like this one. Now this part is made up of silk. Now he flew the kite as high as he could, and you can see in this picture that Sir Benjamin Franklin is also assisted by his son William Franklin during the experiment. Now this kite flew very near to the clouds, and then, as the predictions were almost correct, from the clouds the charges were being drawn. Now it was already raining, so that means the entire hemp rope as well as the silk part was now wet. So these electrical charges, they actually went down and the charge is also gathered in the key. So now this key was actually literally charged, say negative. Because now this entire hem probe was no longer an insulator because it contained water. Now what did he actually do afterwards? You can see in this picture that he brought his finger very near to the key and he felt the electrical sparks. So there were few observations, like you can see the tiny threads on the hem probe, they stood up. Then when he brought his finger, he could see the jumping sparks between the finger and the hand.
And charge, the common SI unit of electric charge is Coulomb, symbol is capital letter C, and CGS unit is ESU or stat coulomb, and 1 coulomb equal to 3 into 10 raised to 9 stat coulomb, that is interconversion. And fundamental amount of charge is the charge of electron or charge of proton, and charge of electron is minus 1.6 into 10 raised to minus 19 coulomb, and proton is having a positive charge of plus 1.6 into 10 raised to minus 19 coulomb. And just see the charge and mass of electron, proton and neutron. I already told you about charge of electron and proton, and see the masses. Mass of proton is almost equal to the mass of neutron, and protons and neutrons are within the nucleus and electrons are revolving round the nucleus in different orbits. Suppose a body is having a positive charge, it means that it has atoms with less number of electrons than proton, and if a body is negatively charged, that body will have atoms with the excess of electron than proton. Just see, there are two types of materials, conductors and insulators. As you all know, conductors means the substances through which electric charges can flow, and insulators means through which electric charges cannot flow. There you can see two examples of insulators and two examples of conductors. When a copper and a steel is connected, the bulb is glowing, but when glass and wood is connected, the bulb is not glowing. Remember, both the conductors and insulators can be charged, but in the case of a conductor, since the charges can easily move through the substance, if a portion of the conductor is charged quickly, the charge will be distributed all over the surface. But in the case of an insulator, the portion wherever it is charged will be charged, and that charge cannot move from one place to another. That is the difference between charging of conductors and insulators. Both conductors and insulators can be charged. Now see this, there are three methods of charging. I already told you, charging means making more number of electrons or less number of electrons in a body. And charging can be done with three methods: charging by friction, charging by conduction, and charging by induction. And in charging by friction means rubbing two objects together, and as seen here, we can see a glass rod rubbed with the silk. Glass is becoming positive and silk is becoming negative. What happens when the glass rod is rubbed with the silk? Electrons are moved from glass to silk, so glass becomes positively charged and silk becomes negatively charged. Rubbing of two objects, electrons getting transferred from one body to another, so that it can attract very minute bit of paper also. Very minute bits of paper. Just see this one. When a balloon is rubbed against dry air, the balloon negatively charged and the hair become positively charged. Now you are aware that positive and negative will attract. So as seen in the picture, you can see that the balloon is getting attracted to the hair, or hair is getting attracted to the balloon, because unlike charges will attract. And see this example, a charged cup, plastic cup is brought nearer to a stream of water, and the stream of water is getting deviated because of electrostatics charging, and see the comb, charged comb when nearer to the stream of water also will be deviated, and this is due to the fact that water is a polar molecule. That means water is having positive and negative charges little separated. So, inherent dipole is there for a water molecule. So, one end is positive and the other end is negative, as you can see here. So, the negatively charged end will be attaching nearer to the positively charged body, that is why the path is getting bent. Now, see charging by friction, I shown you the rubbing of two objects, glass rod and silk. Like that, if any two objects are rubbed, charge can be generated. But see this table, glass, flannel, ebonite and dry hair, and on to the right column we can see again silk, ebonite and polythene. And when you see the table, you can see that ebonite is onto the first column and also onto the right column. That means when ebonite is rubbed with the flannel, ebonite become negative and flannel become positive, but when ebonite and polythene are rubbed together, ebonite is becoming positive and polythene is becoming negative. Because when you rub two objects, the material from which the electrons are, or in which the electrons are loosely bound, is heat to transfer. So, when glass rod and silk, electrons are loosely bound in the case of glass than silk. So, glass become positive due to the movement of electron from the glass to the silk, and but at the same time ebonite when rubbed with the polythene, from the ebonite electrons are moving to the polythene. So, like that we can arrange the substances in an order which will give the polarity of the bodies, and that series is known as electrostatic series. We can arrange all the substances in a line or a column, and from this electrostatic series we can understand which body become positive and which body become negative. See the electrostatic series, glass rod is coming top of wool. So, when a glass rod is rubbed with wool, glass become positive and wool become negative. So, at the top, materials at the top become positive and materials at the bottom become negative. Now, let us see the next method, charging by conduction. And in the conduction, the materials to be charged must be in contact with the charged body. As seen here, you can see that an ebonite rod rubbed with the flannel is already having negatively charged body, and when it is touched with a neutral conducting sphere, the conducting sphere is becoming negatively charged due to the contact between the ebonite rod and the metal sphere. So, in this case, both the charging body and the body which is to be charged is getting similar type of charge. And see this one, a small pith ball is hanging, and that is neutral ball. And when the neutral ball is touched with a negatively charged ebonite rod, and see the second figure, they are in contact. So, due to the contact, the negative charge of the ebonite is getting transferred to the ball, and later on, see the last picture, later on they are repelling, because like charges will repel. That is charging by conduction. In charging by conduction, both the bodies are getting similar type of charge. Next method is called charging by induction. And in induction, as you can see, the material to be charged is not made in contact with the body used to charge. Say for example, ebonite rod rubbed with this flannel is kept nearer to a neutral sphere, and the nearer end of the sphere is getting positive charge due to the repulsion of electrons away from that end, and that electron is getting accumulated to the other end. So, this will happen when the body is brought nearer to the charged body but not in contact. In this case, both the bodies, that is the body to be charged, is getting opposite polarity. That is, if you are using a negatively charged ebonite rod, the body will be getting positively charged. And this is another simple example. A positively charged man coming nearer to a neutral body, the electrons from that neutral body is coming closer to the person's end, and the other end is having positive. And see this another case, the different methods I will show you here, the different methods of charging by induction. And in this case, say first body to be charged is kept on an insulating stand, and as seen here, a negatively charged body is brought nearer, positive charge is getting nearby and negative charge is getting other side. Now you can slowly touch the other end with your hand, and that method is called earthing. And earthing means we are connecting that end negative to the earth so that the negatively charged can flow to the earth. Now remove the hand and the negatively charged body, the positive charge will be distributed uniformly onto the sphere, and this is one method, that is by earthing. And one more method I will show you. See this one. Two metallic spheres are kept on an insulating stand, on separately insulating stand and kept in contact. Say let A and B, and nearer to a negatively charged body is brought. So A becomes positive because of movement of electron away from it, and the sphere B will get negatively charged. Now what should do? Separate the two spheres and remove the charging body also. So left sphere A becomes positively charged and the right sphere B becomes negatively charged. See this one? Positively charged body and negatively charged body can be produced simultaneously by induction, and if we are bringing a negatively charged body, left sphere become positive charge and the right sphere become negatively charged. Now let us see the properties of charges, and as I told you, there are two types of charges, positive and negative. Positive and negative, there exist two types of charges, positive and negative charge, and that is the first property. And next property is that symbol, like charges repel and unlike charges attract. First property is that the existence of two types of charges, positive and negative charge. And second property is that like charges repel and unlike charges attract. That means two positively charged sphere will repel and one positive charge and one negative charge will attract. Next let us pass on to the third property, that is charge is a scalar quantity. And you are aware about two types of quantities, scalar quantity and vector quantity. Scalar quantities can be expressed fully with the magnitude only, but vector quantities need magnitude and direction for its complete representation. And one example is shown here, distance and displacement. Distance is a scalar quantity and displacement is a vector quantity, like that. Charge is a scalar quantity and mass is also a scalar quantity, but distinction between charge and mass is that mass is always positive, but charge can be positive or negative. Next let us see the next property, charge is additive in nature. Additive means if capital Q is the total amount of charge on a body and it is comprised of three charges Q1, Q2 and Q3, total charge on the body capital Q is equal to Q1 plus Q2 plus Q3. That is, the total charge on a body is the algebraic sum of individual charges, but you have to consider the sign of the charge also. As seen at the last, plus 2 Coulomb plus 5 Coulomb minus 3 Coulomb makes a total of plus 4 Coulomb. That is the fourth property of charge, which is charge is additive in nature. Next, let us see another important property of charge, that is quantization of charge. Quantization of charge. As seen earlier, when a glass rod is rubbed with silk, the minimum charge on the glass is plus 1 Coulomb. That means that minimum number of electron which can be transferred is 1 electron. That means we cannot transfer half an electron or 1/3 of an electron, so on. And that fact is that the charge on the body is integral multiple of the fundamental charge, which is same as charge of an electron. That is Q equal to plus or minus Ne, where Q is the total charge on a body and N means integers, it can be either plus or minus. For example, if charge on a body Q is equal to minus 3e, means that the body is negatively charged and it is having 3 electron extra. Like that, charge on a body can only be integral multiple of charge, fundamental charge, and that fact is called quantization of charge, which is yet another property of charge, which is a quantization of charge. Now, another important property, charge is conserved, and you are aware of law of conservation of energy. That means energy can neither be created nor be destroyed, but it can be transformed from one form to another. Like that, charge is conserved. For example, I am taking the same example, when a glass rod is rubbed with the silk, glass and the silk form a single system and the total charge on the system is constant. If 2 electrons are getting transferred from the glass to the silk is getting 2 electrons, but glass is losing 2 electrons, so that the total charge of the system is conserved, and that property is known as law of conservation of charge. That means total charge of an isolated system always constant, which is an important property of charge. Now, I told you about 6 different properties of charges. Charge are only 2 types, positive and negative. Like charges repel and like charges attract. Charge is additive in nature. Charge is quantized and charge is conserved. Now, let us see the force between any 2 charges. And the force between 2 charges is formulated by a scientist whose name is Coulomb. Full name is Charles Augustin de Coulomb. And he formulated an equation for force of attraction or repulsion between any 2 charges. And he made the fact that the force between any two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So, larger is the magnitudes of the charges, larger is the force, and farther is the distance between them, lesser is the force between them. So, when you combine both the proportions or statements together, you will get equation for Coulomb's law. F is directly proportional to Q1 into Q2, F is inversely proportional to R square. So, you can write F directly proportional to Q1 into Q2 by R square, and the constant of proportionality is small letter k. So, the equation for force can be written as vector F equal to k into Q1 into Q2 by R square R cap. And you are aware that R cap represents the direction of the force, which is a unit vector in the direction of force, and vector F gives the force, electrostatic force, which is a vector quantity, electrostatic force. And the constant of proportionality is known as electrostatic force constant, or simply Coulomb's law constant. So, equation for force can be written as vector F equal to k into Q1 Q2 by R square R cap. Now the magnitude of the force shows that force is inversely proportional to the distance and force is directly proportional to the product of the charges, and this can be represented graphically like this. On to the right you can see the graph between force and product of the charges, which is a straight line sloping up, which shows that force is directly proportional to the product of the charges, and left hand side picture you can see that graph which is a parabolic in nature, which shows that electrostatic force is inversely proportional to the distance. Larger is the distance, lesser is the force. So Coulomb's law equation, vector F equal to K into Q1 into Q2 by R square R cap, and magnitude of the force is F equal to K into magnitude of Q1 into Q2 divided by R square, and see the last equation, R cap can be written as vector R divided by R. So another form of electrostatic force is vector F equal to K into Q1 into Q2 by R cube into vector R. And the value of K is, I already told you, K is the constant of proportionality, which is named as electrostatic force constant or Coulomb's law constant, and the value of K is 1 by 4 pi epsilon 0, where epsilon 0 is known as permittivity of free space. That means how that medium is permitting the force between the two charges. I will give a simple example. If the two charges are kept in air and if the same two charges are kept in water, the electrostatic force between them will vary, because the permittivity of the free space is different from that of water. So epsilon 0 is known as permittivity of free space, whose value is found to be 8.85 into 10 raised to minus 12 Coulomb square per Newton meter square, and that unit is obtained from the same Coulomb's law equation. And when you substitute for epsilon 0 in the formula for K, which is 1 by 4 pi epsilon 0, the answer for K is found to be 8.98755 into 10 raised to 9, and approximately it is 9 into 10 raised to 9 Newton meter square per Coulomb square is the value of K. And remember, that is an SI system when the two charges are kept in air or vacuum. So simple equation for Coulomb's law or the force between any two charges in SI system can be written as 9 into 10 raised to 9 into Q1 into Q2 by R square. So from this equation, when Q1 equal to Q2 equal to 1 Coulomb and R equal to 1 meter, from the equation we can get F equal to 9 into 10 raised to 9 Newton. This equation can be utilized for defining the SI unit of charge, which is Coulomb. That means the charge on a body is said to be 1 Coulomb if it repels another identical charge kept in air or vacuum and experiences a force of 9 into 10 raised to 9 Newton, which is the definition for Coulomb, which is the SI unit of charge. 1 Coulomb defined from Coulomb's equation. Now let us see the vector form of Coulomb's law. I already told you about the equation vector F equal to K into Q1 into Q2 by R square R cap, and in vector notation, just see the picture.
Let the charges Q1 and Q2 be at positions specified by the position vectors R1 and R2 with respect to the origin O. The vector R21 is equal to R2 minus R1 joins Q1 and Q2. The force on Q1 due to Q2 is F12. The force on Q2 due to Q1 is F21. In vector form, we can express Coulomb's law as shown. If Q1 and Q2 are like charges, they repel. In this case, the product of the charges Q1 and Q2 will be positive. The unit vector R12 cap is given by equation 5. Here, the force F12 will be in the direction of the unit vector R12 cap. If Q1 and Q2 are unlike with respect to each other, the force F12 will be in the direction of the unit vector R21 cap as given in equation 6. Since unlike charges attract each other. In this case, the product of the charges Q1 and Q2 will be negative.
Similarly, F21 is the force exerted on the first by the second, and we can show that if force on Q2 due to Q1 is F21 and F21, see the expression by Coulomb's law, K into Q1 Q2 by R21 square 21 cap, and if Q1 into Q2 is greater than 0 means that one is positive charge and the other is also a positive charge, then they will repel. So if Q1 into Q2 is greater than 0, they are identical charge because plus into plus become plus and minus into minus also become plus. So if Q1 into Q2 is greater than 0, both the charges will repel. And if Q1 into Q2 is less than 0, that is negative, means that both the charges are unlike and they will attract. So F12 is equal to K into Q1 into Q2 by R12 square R12 cap, but from the vectors vector R21 and vector R12 are equal in magnitude and opposite in direction, so they can write vector F12 equal to minus of vector F21, which is as per Newton's third law. For every action there is an equal and opposite reaction, which is the Newton's third law. So Coulomb's law agrees with the Newton's third law, which shows that if the charge A is experiencing a force on B, B will exert equal force on A. So if two charges Q1 and Q2 are there, the force of attraction or repulsion given by Coulomb's law, F is equal to K into Q1 Q2 by R square. But if more than two charges are there, as seen there, you can see many number of charges, Q1, Q2, Q3, Q4, all the charges are in the field of one another. So the entire total force on any one of the charge, say Q1, can be determined by superposition principle. We have studied in 11th standard already. Superposition principle states that if a charge is surrounded by many charges, the total force on any single charge is the vector sum of the forces experienced by other charges on the first. As seen here, you can see that Q1 is the charge and Q2 and Q3 are kept nearby. So the total force on the first charge vector F1 equal to vector F12 plus vector F13 shows that vector F12 is the force between 1 and 2 and vector F13 is the force between 1 and 3. So when you substitute the Coulomb's law, the total equation can be obtained like that. Like that, if any number of charges are there, and see this, if n number of charges are there, we can use the summation. So vector F1 equal to vector F12 plus vector F13 plus etc. up to vector F1n. Like that, we can find the resultant force on any number of charges using this principle of superposition. Now I am just winding off till here, and the remaining chapter I will take in another class. Thank you.